All right. So this week we're going to look at Chapter 8. Test is next Thursday. Remember right? Normally it's on 6, 7, and 8. So we're going to look at the normal distribution curve. Everybody should have one of these sheets. No, you're fine. People snuck in after it, like when I was handing out, so it's fine. If you got one of the first ones, there's 2 sheets. You need them both. If you got one of the later ones, it's double-sided. So we're going to talk about that. Don't freak out. It's actually a lot easier than it looks. It's a lot of numbers, but it saves you a bunch of calculations, which is the key. So the normal distribution is that nice bell curve. So that we've seen or that you hear about all the time. That's what we're going to be looking at. So one of the things in Hawks, if you notice, there was a unit that I moved. It's because I didn't cover the z-score and stuff like that. We're going to do that today because it was covered and then, or it was supposed to be covered, and then there was like 4 or 5 chapters after that point that you didn't use it at all, and then we covered in Chapter 8. So I'm like, there's no point in me talking about it a month or so ago, and then I'm going to have to refresh your memory anyway when I'm doing Chapter 8, so I just move it to Chapter 8. So that's why that 1 unit seems out of place.
4.2.
Yeah, or 4. It's 4 point something.
Wasted a lot of time.
Yeah, I moved it to the end because we're going to literally do it now. So that's why that's there. All right, so these bell curve, one of the things that you'll notice about the bell curve is it's symmetrical. So the middle of the bell curve is your mean, your mode, and your median. So this point right there is your mean, your median, and your mode. So when we're looking at a bell curve like this, we only need to worry about the mean or the mean. So everything's going to be focused on the mean. Because it's symmetrical, they're in essence all the same. The other thing that we've been talking about recently was the standard deviation. When we're finding the standard deviation, that tells you how much spread there is. So on the bottom, you'll see these numbers here. Those are how many standard deviations away from the mean you are. So these are the standard deviations. So that's 1 standard deviation, 2 standard deviations, and 3 standard deviations. The other direction is -1, -2, and -3 because it's counting from the middle. What you see on the screen right there is known as the empirical rule. Because there's lots of ways we can do the calculations out, sometimes we just want to know a general idea of what's going on. 1 standard deviation away from the middle or from the mean is 68% of all information. So all data or all scores or whatever we're looking at is within 1 standard deviation of the mean. Within 2 standard deviations of the mean, we have 95% of all the data. And within 3 standard deviations of the mean, we have 99.7% of all the data. Okay. So you'll notice that when we get out to 3 standard deviations, that's basically everybody. Okay. So you're talking a 3 out of 1,000 that don't fit within 3 standard deviations. So when you're talking about data and information about individuals or people and things like that, when you get out that far, you're basically talking about everybody. All right. That's why we don't need to go much further than that. You get out to 4 standard deviations, we're talking 1 in 10,000 that would fit within 4 standard deviations. Okay. And we're going to actually see some good use cases of that in a few minutes. So another way that they break this down is they'll split them up into pieces. So we can have like that 68 split into 34 and 34, and then so on and down the foot. Yes. It's slightly, so you'll notice that this is known as the empirical rule. It's like, it's a general idea. It is not exact. And when this is what this table right here that we're looking at, this is going to give us the exact values of everything we need. So, and that's where it's, some graphs you're going to see, and that's why I chose the other one. You'll see how it's slightly different. It's a lot easier to say 68, 95, 99.7 than 68.2, 95. It's a lot harder to say that. So some of the times when you're looking online, you're going to see these type of graphs where it's going to have it split up. If I wanted to see just this side of the graph, what percentage of data is on that side of the graph? Yeah, 50%. So we have the graph, it can be split in half. 50% on one side, 50% on the other side. That's what's known as symmetrical. If I wanted to go up to this point here, we would just add the other 34%. So that would be 84%. Okay. So when we're looking at doing a very simplistic case, which is what you're going to kind of see in that first unit of 8.2, where it's very simple, that's some of the stuff they're talking about. That's also some of the stuff that you're going to see when you're looking at that, whatever, for 4.2, whatever the section was from the other one. It's very simple situations. We're going to get into the more complex situations today and using the table. But honestly, even I'm saying more complex, it's just because the numbers aren't always going to be nice. I'm not going to ask you for one standard deviation above or one standard deviation below. We're going to look at like 1.2 standard deviations and things like that. So that's really where I'm saying a little more complex. It's not actually, believe it or not, that much harder. All right. So when we're looking at the curve and we're looking at all these spots here, those numbers are telling me how many standard deviations I am away from the mean. That's known as a z-score. So a z-score is going to tell you how many standard deviations you are away from the mean of whatever data we're looking at. So your z-score formula is whatever value you're looking at minus the mean divided by the standard deviation. It is always x minus mean divided by standard deviation. Yes. Does it have to be written that way with a little line through it? Oh, no. That's just so it doesn't look like a 2. Okay, so that's z-score. We're going to use that now. We'll talk about those later. All right. Anybody in here know how high a door is? Close. 80. So a door is exactly 80 inches high. Why? Yeah. So, okay. So would the door height be different in Norway? Why? Yeah, they're taller. Norway is actually the tallest country in the world. So when you're looking at, Connecticut's a great situation for this, because if you go into any of the really old houses, the stairs are smaller, the doorways are smaller, because again, people were smaller back then. We've now standardized a lot of that stuff. And actually, if you've ever tried to walk up and down some of those old stairs, you might trip because they're not exactly 7 inches by 11 inches, 7 inches high by 11 inches wide, which is the standard now. Yeah.
My dad has an old house like that, so the steps are super narrow.
Yeah.
But yeah, it's awkward to walk in.
And when they were doing it, it was to save space because they used the areas of the houses different, because it was like building things were done differently back then. So our bodies are so attuned to walking on stairs that are exactly 7 inches high and 11 inches wide that if it's off by even like a quarter of an inch, you're going to stub your toe and trip because it's like you're just used to that step height. Doors are exactly 80 inches tall. They're designed that way by code because of this. So in the United States, the mean height of a male is 71 inches tall, okay, which would be 5'11". That is the mean height of a male in the United States, with a standard deviation of 2.7. Okay. So the mean right in the middle, 71 inches. So how tall would somebody that's one standard deviation above be? How tall would one standard deviation above the mean be? Yeah. Yeah. We're going to take the mean and we're going to add 2.7. So it'd be 73.7 inches. Two standard deviations. We would add another 2.72. And we'd get 76.4. Yeah. Three standard deviations. I would add another. Close. 29.1. 79.1, yeah. 79.1. Huh?
So vaguely 80 for the
So 80 is a little higher. But remember, we're going to talk about that in a second. We'll get that one in a second. If I went the other direction, I would subtract the 2.7. So this would be 71 minus 2.7. I'm not doing subtraction in my head. $68.3. And then this would be 65.6 and 62.9. All right, so we have, that's in essence how you can break down your standard deviations in your bell curve going up. So we can now say, crazy it's gonna sound, how much is between -1 and 1? What percentage? Almost, that's half. 68. Remember, 68 was one standard deviation. So 68% of all males is between 68.3 and 73.7 inches tall. So 5'8" to 6'1" is 68% of all males. 95% of all males is between 65.6 and 76.4. And then 99.7 would be between 62.9 and 79.1. Okay. That makes sense? All right. So how many standard deviations would 80 be? I used the those numbers actually were Norway. Was it 71 point or 71 exactly? I want 80 inches. So let's do my z-score to figure out where that's going to be. So I would do 80 minus 71 over 2.7. I'll go do it in a second. They updated the computer. I had it blocked so that the screensaver would not come up. And it's not helpful.
Where is my thing? There. Okay, I guess I'm just gonna have to come and click on this every so often.
All right, so we got 3.33 standard deviations. Okay. All right. So just over 3, not that much further, but just over 3 standard deviations away from the mean. Okay, so now let's use this. Everybody has one, right? Okay. So notice on the side here, we see Z. On one side or one sheet of the paper, you have a whole bunch of negative Z's. And on the other one, you have a whole bunch of positive Z's. Is my 3.33 positive or negative? It's positive. So we're going to go to the positive side. And we're going to go down until it says 3.3. Now, I want the other 3. That's what this second decimal place is up top here. Okay? So this is the third decimal, basically the second decimal place over. So I want 3.33. So I'm going to go down the 3 column all the way down to 3.3. And I would get negative 0.9996. Everybody find that on their sheet? So you're going to go over to the column that says 0.03 and go all the way down to where it says 3.3. That's how you get 3.33. Okay. This class will be very, very difficult if you can't find these numbers. So I really need to make sure that everybody can find these numbers. If you didn't, yes, you're going to be allowed to use these when you have a test. So everybody in here was able to find the number? Good. All right. What that number means is, if we look at this sheet here, it means from here all the way over to my number there. There we go. So it means all the way over to where that's 80. So that would be a z-score of 3.33. Okay, so that's all this filled in. And we got, what was it, 0.9996? Oh, 9995. Oh, no, it was 9996. The numbers start off at 0, not 1. It's okay, because that's why I looked. I'm like, oh, that was the mistake. Yeah, so 0.9996. So that means that under an 80-inch door, 99.96 of all males will be able to walk under that door. Okay? So 4 out of every 10,000 men will hit their head. Women heights are typically lower, so their z-score would even be higher than that. So it'd be like 1 out of 100,000 or something like that that actually would fall under that situation. So that's why the 80 is the standard height of a door. So there's reasons for everything. And somebody actually did all the calculations, come up with this to figure that out. Whenever you get into an elevator, there's a sign inside the elevator. Does anybody have a guess of what the sign says? Not the numbers and everything else. I don't think it says watch your head.
The weight limit?
It says the weight limit. It'll typically tell you a weight limit, and up until recently, it would tell you the number of people. Okay, so that 10 people and 200,000 pounds or whatever else it is again based off of the mean and standard deviation of a typical male because again, males are typically heavier, so they use their weights to figure out how many people could go in the elevator. There was a situation in New York a long time ago. It was a ferry boat. So this boat went out and would have normal people. So they would be able to take like 30 people onto this boat. Well, the captain booked a bachelor party. And they put 30 men on this boat, and the boat sank. Because all the calculations were done based on the average of everybody, not just males. So when they were assuming 30, they were assuming an equal distribution of male and females on the boat. So the weight limit was way over when they put on 30 males onto the boat as compared to just 30 people that would normally be going out. So that's why understanding the calculations, that's why I said a lot of times down your elevators, they will not have a number of people. It will literally just be the weight. Okay. And there's tolerances in it. It's not like if you hit 2,001 pounds, it's going to crash. There's tolerance built into it, but that's why that number is there, because that's how they calculate these things. So you can start to see how the stuff that we're looking at now actually does impact everything that we do, and everything, and all building codes and everything else that we have is done. And if you go to some of the Asian cultures, they're typically smaller. So their houses and their structures and their doors and everything else will be built smaller than we do here in America. Yeah.
I think it's funny when like any sort of like home design channels will show like a smaller house, and you just see all the like American visitors like
They're ducking their heads and everything else. Yeah. Exactly. It was like we were over in Ireland, and the Airbnb we rented, the shower head was basically like at my forehead. I literally had a duck to get into the shower head. And it was like, this is not normal, but that's building codes are a lot different over there. All right. So let's look at some other ways to use this sheet. So this sheet is giving me a probability. It's giving me a percentage. That's what all these numbers in the middle there are, is that probability. All right. So I want to compute the probability that a random variable is going to be less than 1.27. So this right there, that is my z-score.
okay, so 1.27 standard.
Yes, that is my z-score. So that means right there is 1.27. I want to find less than that. So I'm looking for the percent of all this colored in over here. If you notice at the very top of your sheet, what is the little curve? How is it shaded in? It's shaded in from the left over to that value, correct? So this sheet is going to give you the numbers all the way from the left to whatever Z you're looking at. Okay, so in this situation, the problem that we're looking at, that's what I want. I want from the left all the way over to that line. So find me 1.27 on that sheet. So I'm going to actually copy this. Yes.
So because it says less than, does that mean we would go down 0.1, or we would just use the other one as a bending point?
Oh no, you're going to use 1.27.
Okay.
All right, so 1.27. So we're going to go 7 and 1.2. So that means it's that number right there. These sheets will always have the 0 on the left, so you have it's 0, 1, 2, 3, not 1, 2, 3, and then the zeros at the end. So 1.27 is 0.8980. So the probability that will be in there is 0.8927. I moved down. 8980. So that is the probability that the variable is less than 1.27. Yes.
So just for the phrasing, we'll probably get like on the test. I assume it asks like that a standard rate.
I will actually specifically state the Z-score and stuff
Okay,
on the
okay.
test. I do not like how this question's worded because it's very weird.
So vague.
Actually, the majority of the questions you're going to have on the test, you're going to have to find the Z-score. So this test will be a lot of word problems.
Are we doing Chevy Chevs?
No, no. We're not using Chevy Chevs at all. Chevy Chevs rules came out prior to the empiric rules. It was a little more generic. So yeah, we're not using his at all. All right. What if I wanted to find a variable between 0 and 1.27? So I want to find it between here and 1.27. So I'm just looking for this spot in here. How do you think I would do that? Yeah.
I assume we need to know the probability of it being on 0, like of the mean itself, which would be 50.
Right. Okay. So we know from this problem right here that the whole thing is 0.8980, right? Correct. So I know that the whole thing is 0.8980. And this part over here that I don't want is 50%. So then the answer in the middle, this part, would be 0.3980. Okay, so that one's simple, right? Look at your table and find the z-score of 0. What does it tell you? 0.5, 50%, or 0.5000, right? So that's how we'd find something between 0 and 127. What if I wanted it greater than 127? What if I wanted this section over here? Why? Correct. So that's the complement of what I want, right? So in this case, I'm going to do 1 minus 0.8980, which would give me 1020. And that's it. So if I'm looking for the opposite direction, I just take whatever the number is and do 1 minus it. So you'll notice that the biggest thing when you're looking at these is where you're shading. Okay, so when you're taking these pictures, and what my suggestion would be is if you have a printer, print out a bunch of these little blank ones when you're doing your problems. This way you can put your numbers on there and shade where you're looking for. Okay, because it's really easy to screw up which direction you're going. And by shading, once you shade it, it's like, okay, it's going to click. It's like, all right, I need to subtract from 1, or I need to subtract these 2 things. Like that's the piece that's going to really come out into play. Okay? All right. Try this one. So that's what we're looking for. All right. So if you looked on your sheet, negative 1.08 should give you 0.1401. Where does that value go to? Which part on this graph is it giving me? 1, 2, or 3?
Like it's giving you the cutoff point.
Right. It's giving me from the left over to negative 1.08. Is that what I want? No. So how am I going to figure out in between those two?
You subtract from 0.5.
So we find them both. Or in this case, because you should know the 0 is 0.5, but so this one right to there is 0.5, right? And that's from there all the way over to there. And this all the way over to there is 0.1401. I want in the middle here. So we subtract those two numbers. And we get 35.99. So that would be the space in the middle. So now you can start to see why shading and looking at it and recognizing that the table is always going to give you from the left over. Okay.
I did it with positive one first and that.
Well, yeah, if you did the positive one, it's going to be, yeah, it's going to mix you up.
Did you find the complement and then subtract, I don't know, half of the median or something? I don't know. I was going about it really complicated. You know?
Yes, if you found the complement, you get this section over here, and then you'd still have to subtract half of that.
Take away.
Yeah, so you'd have to. So you're doing an extra, and that whole extra calculation to do basically the same thing. Yeah, but that's the thing. It's like there's lots of different ways you can do the calculations. Like you can go around the circle and get it, and that's fine. Key is getting it. Maybe not the fastest way, but you got there. All right. All right. What about between 1 and 2? We're looking in there. So looking for 1 and looking for 2, those should be the numbers you get. So how would I find in between those two? Just subtract it. So it's no different than the last one we did. 1, 3, 5, 9. Except this one, we didn't have the 50%. Yeah.
The box ever asks for the answer as a percentage?
It shouldn't. If they ask it as a percentage, I believe they put the percent sign there. So you would just be able to move the decimal, but it shouldn't. It should actually.
It's like iffy about rounding.
Yeah, see, these aren't rounded. So the nice thing is actually the sheet that I gave you is the exact same one as Hawks uses. So you're fine. There was actually another sheet that I used that had 5 decimal places that was a little different than Hawks, and that was causing some issues. So this is the same as the one that's in Hawks. And actually in Hawks, when you're doing the problems, they actually will give you the table. You can click on it and say, see the probability table. So you could technically even use their table for it. But their table is going to look the same. It's going to have those 4 decimal places. It's going to be rounded the same way. So there shouldn't be any issues in terms of that rounding errors. That's one of the nice things about doing these is you're not really doing a lot of calculations that are going to cause you to round, except for the Z-score.
I assume in the wording when it says like standard normal random variable, it means
It's going to give you the Z. Yeah, that's the Z-score. So, yeah, that seems to be their definition for how a Z-score is. All right, what's my next problem? This is more how my test questions are going to be worded. Find the probability of a normal random variable with a mean of 10 and a standard deviation of 20 that'll lie between 10 and 40. So, all the ones so far that we've done, they gave me the what? They gave me the Z-score, correct? They don't give me the Z-score in this one. So what do we have to do? We have to find it. The only way we can use that sheet is with the Z-score. So we need to find our Z-score. So what's the formula for a Z-score? Over. So my mean is 10. My standard deviation is 20. I have 2 X values. I have 10 and 40. So we have to do it for 10 and we have to do it for 40. Your Z table sheet will always be rounded to 2 decimal places. Okay, so when you're looking for your Z score, you're always going to round to 2 decimal places. We're looking at between 0 and 1.5. So what do we get? That's the 1.5, right? And the 0 is 50, right? So how do I find between them? I subtract 0.4332. Yes.
Will any of these problems be phrased with the, I forget what they're called, the, greater than, less than signs?
Not these. We will get to those, but not these. All right. There's what I want. Let's do the other direction. Actually, Hawks might, so I'm going to actually do one of those right now. So let me actually do a couple problems that are very similar to the Hawks questions because it's right from their homework. Okay. So one thing you're going to notice when they do have the less than or equal to ones on there, it'll always be less than or equal to. It'll never just be less than. Okay. So you're always going up to whatever numbers they tell you. So there's no issues with that respect. All right, let's do the ABCD. All right, so actually, I think I have that over here. So what is the probability for negative 1.2 or less than 1.28? So negative 1.28 is what? Good. So that would be that answer, right? Because that's less than. That's from that's this value in here. That would be what less than is. What's greater than 1.28? Huh? Why? It is the exact same thing. Question is why? What did I say about the graph at the very beginning? It's symmetrical. Okay, so both sides are the same. So this section over in here is the same as that section over in there. Okay, they're both 0.1003. Which means, so this might be confusing. So if you easily get confused, shut off your ears for a second. That means if I'm looking for this section over here, I can use the negative side of the graph and I don't have to do the complement of it. It saves you some work. It will always work because the graph is symmetrical. Okay. All right. So what is between those two then? And can I use what I've already found to find that answer? So if I want to find what's in here, yeah. Go ahead.
I think you just add the. Oh wait, no, I'm doing this. Hang on. You can call in someone else.
Okay. Anybody have an idea how to find the middle? Yeah.
Two numbers together and take one and subtract.
I want the complement of what I've already got, right? I want the inside and I already have the outside. So I can just do 1 minus 0.2006, which gives me 0.7994. Or approximately 0.8. So I can easily just do the opposite direction. All right, 2 more problems. All right, so this one says find the z-value such that 0.05 of the area under the curve lies to the right of z. So what side's the right? Is over here, right? This side's the right. So I'm looking for some number over here where that is going to be 0.05. I'm going to give you a minute to try to think.
0.05 as in 0.05, like as a percent.
Mhm.
Okay.
I'm looking for the z-score. They're giving me the percent.
Okay, so this is a percent.
That's the percentage.
Okay.
Or, yeah, it's the probability.
Wait.
It's not, okay, it's 5%
Okay.
or 0.05. It's not 0.05%.
Yeah, that's why I got a little.
No, it's 5% or 0.05. So how am I going to use this table? Am I just going to look at 0.05 and just use that number right there? Because that's Z, right? And I'm looking for Z. So they're giving me the number that's in the middle here. So the question is which number am I going to use?
I assume you subtract the 0.05 to get 0.95 and then
So yes, so that would be the proper way to do it.
the other way is to look at the table and see what's missing or what equals that, right?
So then I get the 0.95. No. That's actually, you're going to need that number on the table. So that's the number over in this section here, right? Because remember, the table is giving me from the left all the way over to it, right? But I want that right side. Okay, so I'm looking at my table now, and I want to find 0.95 in the middle here. So we're going to scroll down until we find 0.95. And you're going to notice there's not an exact 0.95. I'm going to be honest. I have no idea what Hawks is going to want as the answer for this question.
Okay. I was gonna say here.
I'm going to tell you the right answer. I do not know if Hawks is going to want this number or if they're going to want one of the two answers because
the averaging or
so the numbers right there is it's literally right. Okay, so typically that's actually exactly what we're going to do. So typically you're going to choose the one that is closest to it. Okay, so for example, if this was a 4 right there, I'd pick 9505 because it's closer to the answer. Okay, but in this case, they're exactly the same. So the proper answer to this question is 1.645 because this would be 0.04 and that would be 0.05. So you literally go right in the middle of that. That is only the answer though when it's directly in the middle. That number actually is going to become a very, very important number for us going forward. You're going to use that number a lot. So that's what I'm saying. So I know the vast majority of Hawks answers, they want the one that's closest to it. I don't know if they want 1.64, 1.65, or 1.645. So that one I'm not actually sure. The correct answer is 1.645. So I would try that first. So the question is what twofold. One, does everybody understand why I found almost? Does everybody understand where I found the 0.95? That's the first question. Okay. You're looking in that middle of the table to find that number. So you're looking inside, not on the ends. Once you found where that number shows up, then you find out the z-score that goes along with it.
You're just using table backwards, basically.
Basically, yep. You're looking at the table underneath. All right. I think actually that's where I'm going to end it today.